Number 23 is going to be our first example of a partial fraction decomposition that has a quadratic factor, an irreducible or unfactorable quadratic factor, the x squared plus 9. That just means when we do our partial fraction decomposition, we need to be a little bit more careful. Our denominator is already factored, and this rational function clearly meets the degree requirement since the degree of the numerator is 0. Just remember, when we do a partial fraction decomposition, and one of the factors in the denominator is an irreducible or unfactorable quadratic, we set up its numerator a little bit differently. If your denominator is linear, such as x minus 1, then your numerator is constant, so we'll put an A up there, capital A. If your denominator is quadratic, irreducibly quadratic, then its numerator is a generic linear expression, so we could put something like capital BX plus capital C, or whatever letters you want to use if you're not comfortable using plus C in this capacity. All right, let's clear out the fractions. I probably should have said this in the first video, but on all of them, if you would like to pause the video and try to do the problem before I go through it, by all means, do so. It's easier to follow me while I'm doing it than it is to try to do it on your own and see if you're right. So think of it as an opportunity for individual practice. Again, I should have mentioned that, 4 videos ago. All right, let's see what we're left with. On the left side of the equation, we get 10. On the right side, we're left with A. The x minus 1s cancel, leaving us x squared plus 9. And on the right side, the x squared plus 9s cancel, leaving us bx plus c and x minus 1. All right, our plan to substitute values for x is going to be a little bit challenging because we can only make one of these factors equal to 0 without resorting to complex numbers, and that would be the second one, the x minus 1. But that's a good place to start. If we let x equal 1, the left side of the equation is 10. Putting 1 here will give us 10a. And then putting 1 here will 0 out because putting 1 here gives us a factor of 0. So that instantly gives us a is equal to 1, so that's good. But now what do we do? The only numbers that will make the second factor, x squared plus 9 equal to 0, are imaginary. So we don't want to go there. So let's just pick some values and see what happens. X equals 0 sounds good. Let's see what happens when we put in 0. Remember, a is equal to 1. When we put 0 here, we get 9 for x squared plus 9, and a is equal to 1, so we just get 9. Of course, it would help if I write the left side of the equation first. 10 equals 9. When we put 0 here, we just get c, and when we put 0 here, we get negative 1. So together, that makes a minus c. So let's just put minus c here. Okay, this wasn't too bad. This implies that c is equal to negative 1. If you don't see it, check your arithmetic. We'll put our constants, our numerators, in red boxes so I can find them when I need to. Okay. Now to find b, we just need to pick another value for x. I'm going to let x equal 2 because that will make this 1. I can pick any number, but I think 2 is good. Now the left side of the equation is still 10. Okay, on the right side, we're putting in x equals 2. 2 squared is 4. 4 plus 9 is 13. A is 1. 13 times 1 is 13. Plus. Now when we put in 2 here, well, first off, when we put in 2 here, we get 2 minus 1 is 1. So 1 times anything is itself, so we can just focus on putting 2 here. But remember, the c is negative 1. So if we put in 2 for the x, we get 2b minus 1. If we combine the like terms on the left, we get 10 equals 12 plus 2b. Subtract 12 from both sides, we get negative 2 is equal to 2b. And this implies that b is equal to negative 1. All right, so we have our missing numerators. It's supposed to be a box. We have our missing numerators. I can get the tool to work. There we go. All right, a is 1. It goes on top of this fraction, so we get 1 over x minus 1. B is -1 and C is -1. So when we put both of them here, we get negative x minus 1 over x squared plus 9. And all this dx. What I'm about to do is not necessary, but I think it'll make the problem look better. Notice that in the second fraction, the numerator, all the terms are negative right here. I think factoring a negative out of that and making them all positive is a good move. We factor the negative out and put it in front and change these to positive. I think it's not a bad idea. And again, just make sure you're clear about the move I just did. All I'm really doing on the top is factoring out a -1 and then pulling it out of the fraction and multiply it in front. So we would get minus, and in the numerator, just an x plus 1. All right, so we have our partial fraction decomposition. The first one I'm not really worried about. It's just going to be natural log of x minus 1. It's the second one that we're going to have to dance around a little bit. Let's clear out the partial fraction decomposition and then continue. All right. As I mentioned, the first integral is pretty straightforward. The integral of 1 over x minus 1 dx technically requires u equals x minus 1 to transform it into the integral rule. The integral of 1 over u du equals natural log of absolute value of u. But if we let u equal x minus 1, then du equals dx, and so we don't really have to worry about doing the substitution. And just call this what it is, which is the natural log of the absolute value of x minus 1. Plus c if we were doing it by itself. We're going to embed it in some more results, so there'll just be one big plus c at the end. Now, as far as the other integral, this guy, we'll bring in the minus in a moment. When you see an integral of this format, where you have x squared plus a number on the bottom and a linear numerator like x plus 1, the strategy is typically to split into two integrals by splitting it across the numerator. Because the one on the left we can do with a substitution. U equals x squared plus 9. Du is equal to 2x dx. So we would need to balance a 2 and a 1/2. And that would give us 1/2 natural log absolute value of x squared plus 9. The absolute value is not really necessary there because x squared plus 9 is already positive for any real values of x. And the second one would be an arctangent. Remember the rule for arctangent is the integral of 1 over x squared plus a squared dx is equal to 1 over a arctangent x over a, and of course plus a constant of integration. In this case, a is equal to 3, since 3 squared is 9. And so we just got to change all the a's to 3's and get 1/3 arctangent, or if you prefer it, tangent inverse of x over 3. We have the answers to all of our integrals. Just keep in mind that the second integral had a minus in front of it. So that minus is going to get distributed across that addition problem. Each half of it will become negative. And so our final answer is natural log absolute value x minus 1. That was from the first one. Minus 1/2 natural log absolute value of x squared plus 9. Minus 1/3 arctangent x over 3 plus constant of integration. I suppose if you wanted to, and I've been saying this, not really doing it on any of them, you could condense these into a single log. It'd be the natural log of x minus 1 over the square root of x squared plus 9. but I think this is a perfectly acceptable stopping point for this question.